Hello, my name is Van Walworth. It's very good to be able to address all of you today. The topic that I want to talk to you about is what I refer to as some underutilized things that we can do in our rubber molding factory, in our tool design, and our processes to be able to save some money, save some materials, save some time. And these are not necessarily things that you don't know about. It's just the things that I have observed over my career that are underutilized, and they need to be expanded more and considered more in different ways maybe to take advantage of them. And so we're glad to be able to be coming to you. I have a presentation that I'll make from a distance. I always like to be in person. I know many of you and your faces, and it's been a long time since COVID that I was even able to be in India, but I'm glad to be on a remote visitation now, and I appreciate Param being able to organize this through TechnoBiz. I know the hotel that you're in, and I know who the sponsors are, and I appreciate them organizing this, especially Venkatesh. I'll wave hi to him personally. So my presentation is basically about your smart rubber factory. That's what all of this is related to. And specifically, I'm talking about how to exploit some of the underutilized process techniques that you might be able to use to reduce rubber molded scrap and waste. To that end, I have a number of different topics. I'm going to go through each one of these topics during the presentation. There's more. There's a little bit of lag between when I click the screen and when you're able to see it. I'm trying to accommodate that with my things that I'm saying as I say them. So I'm going to cover all of these topics one at a time in the presentation today. First off, one of the things that I feel like is important to do is get the right definition of what scrap and waste is. And so for me, scrap is defined as being a molded part that you want to sell, but you cannot because there's something wrong with it. It's a defective, it has some non-conforming aspect to it. So we want to find ways to reduce scrap. In addition to that, there's engineered waste, whether you're in a compression mold, a transfer mold, an injection mold, or some variation of all of those. We usually have some engineered waste, whether it's part of the delivery system like runners, transfer pads, or whether it is actually excess preform that is coming out of the cavity through flash, things that are required in order to make the part. We have expected amounts of engineered waste, but it's still good to be able to try and find ways to reduce that waste. And then there's incidental waste, as I call it. This might be a purge material that you're using from an injection press. It might be seal leakage that's coming out of injection seals. It might be preforms that you drop on the ground and are become dirtied, and so now you can't use them. Molded parts that you take out of the press and lose, or they fall out of the press. I go around presses all the time, and there's all kinds of parts and rubber on the floor around the press and dirty underneath it and in grease and whatnot. But that's part of the scrap and the waste that can be minimized, and it saves time and money. There's our parts that are lost during demolding. There's parts you have molded flash in places. Sometimes we design our molds so that we have flash in certain places. We can tear it off with tear trims, or in some spots there's not supposed to be any flash at all. Not necessarily flashless molding, but it's just not supposed to be flash at that construction line. And over time, there ends up being flash at that construction line, and then you have to spend time and effort and money to be able to remove that flash. And so that's a form of waste and incidental waste that you really would rather not have. Runner flash pads. If you have an injection runner, you may not have designed a flash pad filling up the whole parting line of a runner. That's incidental waste that you probably don't want, don't need. Parting line flash. We know there's usually going to be some parting line flash, but if it ends up being any thicker than you planned on, that can be a real problem, both not only to remove it, but just the fact that it's there. Then you have non-conforming parts due to cavity damage. So this is a case where that sometimes if you have a multi-cavity mold, say 100 cavities, I find that if there's a damaged cavity, the molder might block off part of it with a tape or something like that to keep rubber from going in that spot if they're using a loader board for compression molds, or if it's a injection mold or transfer mold, they might block up sprues to try to keep rubber from going in that cavity until they have at least 10% of scrap parts, and then they'll say, well, now it's time we need to go out and fix the mold so that we can do all the cavities when we're molding. But in the meantime, all of those cavities have been scrapped. I mean, it starts out 10% if you've got 10% of your cavities that are damaged in some way. And so that's sort of a reason maybe to have designed your molds with removable cavities so that you can replace one cavity rather than having the cavities cut into steel where that you can't remove one cavity and replace it very well. And things like that. Operator error due to inadequate training, and especially this one, shelf life of the compound. People struggle with shelf life. So we're going to look at some of these things and elaborate on them just a little bit more. It might be obvious that one of the ways that we would get rid of, reduce our scrap is to reduce the scrap. But that's still a very underutilized technique, mainly because though it's a noble goal to get rid of scrap and to reduce this amount of scrap, it's often an elusive goal. And it seems like to me, as I have worked with many clients over the years, all over the world in different regions of the world, that if you can't get rid of all the scrap, then it was a wasted effort. And they just live with however much scrap they have, or worse, they just simply raise the price, get the customer to be paying for it, and they live with it. It's now not a financial problem because they're making money even though they're running at 5 or 10 or 20% scrap because the customer's price is paying for it. Well, that doesn't mean you shouldn't be looking at it. It's better to actually take an incremental approach to scrap and actually go ahead and ease off on it to one root cause at a time. And deliberate scrap reduction efforts generally do not start for most companies until the scrap percentage exceeds a relatively low normal, whatever that is for your company and that part. When you have a relatively low normal, maybe you tolerate 5% scrap, maybe you tolerate 10% scrap because the customer is paying for it and you're not losing money. And then all of a sudden it turns into 12% scrap. Now there's a problem and you've got to address it. Well, maybe it should have been being addressed a lot before, because things that become waste or scrap problems usually don't fix themselves. They get worse over time. And if you just leave it alone, it won't get better. It will eventually get worse. And not only that, parts that have been running for some time, the customer may have allowed whatever quality level that you were making all this time, and then all of a sudden there are new demands placed on the company by the customer because they want better quality. Well, nothing's changed. It's just that you're not able to make the better quality that the customer wants. It's not that you got worse at it. It's just that the quality demand and expectation will have increased upon your parts. And so now there's a problem. And now we're trying to figure out what it is that we can do to improve the parts. Maybe we should have been doing that all along. In terms of reducing scrap as it relates to what I call incidental waste, this is the purge that you might use. Some injection parts automatic, some injection presses have an automatic purge, so that between every single cycle, there's a little bit of rubber that comes out. And there are good reasons for that. There are a lot of compounds that you really need to do that for, but not every compound. And then there's the suggestion of, well, how much purge needs to be there, especially when it's a manual purge, when the operator is the one that's going to push a button and let some rubber come out. How much rubber should they make come out? Well, that's often, maybe only 2 inches of rubber would have been enough to purge instead of something that was a whole string of rubber that was a lot at different times. And that's an easy way for excess waste to have been taking place, so that you can reduce some of the waste just by minimizing the purge and eliminating purge on presses and parts that don't need it, because there's a lot of parts that don't need that. The injection world of presses is full of a lot of parts, like for instance on horizontal presses and things like that. They run on automatic. They're not purging rubber. They're running on automatic. And so purging is important to a lot of parts, but not every part, and they should be considered accordingly. And so leaking out of transfer pots, if you have a transfer mold, it's common for rubber to be leaking out of a transfer pot. And so that's the kind of thing that we want to try to figure out how to minimize. We'll talk about that a little bit more later. Some other types of waste that are generally not a deliberate reduction effort until they start costing excess labor time and waste. Excess labor expense. A lot of people doing a lot of something that wasn't in the original design becomes the default trigger to call attention to the waste. And for instance, if your part was made so that the operator was molding the parts at the press and then tear trimming them and then supposedly maybe getting them ready to put in a box, but now the parts are so difficult to demold or so difficult to tear trim and be ready to put in a box that the operator doesn't have time. And so either the time of the cycle is extended in order to allow the operator time to do something, or you have to bring other operators in order to process the parts within the cycle time. Either one becomes an expense that is not necessarily the way it was intended to be run. And so there are ways to reduce that before the excess labor is required. It's one thing to reduce scrap by percentage. And so by percentage gives some companies a deliberate directive that says we need to eliminate the scrap entirely with no tolerance or allowance for scrap percentage reduction. That kind of direction by a company or a manager, it's a demand, all or nothing. It's a demand, and it's great. It's a noble goal, but it doesn't allow for those incremental improvements. Sometimes if you've got 10% scrap or worse, and you want to make it better, then it's possible that there are a series of complex root causes that are involved. And you may have to sort out one root cause after another, and then go to another one, and then go to another one, and slowly root them out in order to slowly, deliberately, consistently work at lowering the scrap percentage rather than having to take on the project that says, we're going to get all the scrap out right now, just fix it and solve it. A lot of times with my clients, I am called in to help reduce the scrap of something, reduce the cycle time, do something to improve the process. And the process and or the scrap is a very complex set of issues. We got to find out really what the root causes of the root causes are, and find out ways to mitigate them, to make countermeasures. And it's often not a simple process. Sometimes it's very complex to weed our way through what these root causes are, trying to get down to zero as close as we can on the scrap issue. Researching the scrap root cause or causes is something that most companies around the world do not do, primarily because they incorrectly diagnose the problem. And so I've spent a lot of time making literature, writing in my books, writing on troubleshooting charts and things, some of the causes, root causes of defects. And there's a lot of defects that can happen to us. Most notably, blisters, air traps, short fills, flow lines, back rind, and a host of other things that are very difficult to get rid of. And those are the top 4 types of scrap problems that everybody in the world pretty much has a problem with, whether it's injection, transfer, or compression processes. And the fixes for those are not always obvious. The cause of those problems is not always obvious. It can be a very challenging thing sometimes to overcome what is a problem. Some of these problems start out with a brand new mold and a brand new part right off the bat. And so you start out trying to solve these problems. That's one thing. It's another problem when you have a part that you've been running for quite a while at a reasonable rate of waste and scrap, and then all of a sudden it starts doing something that it had not been doing. Suddenly there are blisters, suddenly there are non-fills, suddenly there is back rind. There's something that is suddenly wrong with this part that maybe it's the material, maybe it's the mold, maybe it's the press, maybe it's a whole bunch of different things. And something has changed, something has happened, maybe in the atmosphere of the environment, maybe in the operator, maybe in the press, and it sometimes is not obvious at all as to what it is that has taken place. And so deliberate effort and research is required to actually understand the true root cause of root causes. And so we need to get there. There's some that are obvious, And then there's a lot of them that are not obvious as being the causes. And we have to understand those better. And I encourage the people to research this more. It's not a flippant thing to just simply be able to say, well, the root cause is this, because that might not be it, or that might not be all of it. In my career, going around the world talking with process engineers, and I've been in well over 1,000 plants over my career, there's a fairly good known sense that as much as 70% of the scrap parts that you might have during any day typically happen within the first 3 hours of the startup of a shift or a shutdown. Most of it happens then. And the part of the reason that we think we observe that is because the press has perhaps been either open for a long time, and now when you start back up, an equalization of pressure and an equilibrium, I should say, of the thermal gradient across the mold has been lost. And so you're either trying to reestablish it, getting it hotter, or you're trying to reestablishing it, letting it cool down from having been closed for overnight, over a weekend, over something, and everything is just a little too hot. And it takes time for that equilibrium to be reestablished around the press and in the environment of where you're working. And so during that reestablishment of the equilibrium is when a lot of scrap can happen, good or bad, whatever it's doing. So knowing that, if you do know that, if you kind of tend to experience that, it means that if your press has been open for a long time, well, obviously maybe you need to keep it closed before you start, or you need to extend your cure cycle a little bit during the first hour, during the second hour, shorten it a little bit, during the third hour, shorten it a little bit more, and then you can continue on. And this makes a difference if it's a lot of little parts or versus a big part, if it's short cures versus long cures, but the concept is based in that. And once that equilibrium has been reached, then the product tends to work better. But knowing that you might be experiencing more scrap at the front end could tell you something. There are lots of companies that have a policy that when they start up a new shift, when the operator comes on, molds the first heat, they just throw it away. They don't even bother looking at it. They just throw it away. It's assuming that it's going to be bad. And that's not necessarily incorrect process, but one heat throwing it away might not be enough. You may have needed to throw away 2 or 3 heats, or you may have needed to determine, well, why is it that this is bad? Because they're too hot, because they're too cold, and adjust your cure time and temperature accordingly at the beginning of a startup so that maybe you don't even have to throw that heat away. But there are ways to, again, take advantage of an unutilized opportunity to avoid scrap and waste when possible. There's another situation that happens, and that is this, similar to the startup, where there's oftentimes a scrap that takes place, a disruption in the process. Sometimes we have to take a mold out and have it cleaned. Sometimes there were parts that got stuck in the press, and so the press was open for a longer period of time than normal during an equilibrium cycle, and try to get some parts out, or we had to clean a particular cavity because some rubber got stuck somewhere, or there was a sensor or something that stopped the press from being able to just run again in cycle. We had to wait for maintenance to come and tweak the sensor to, or something to the process controls, do something to the press. But the point is, the normal cycle that had established an equilibrium in temperature and pressure got disrupted. And when it got disrupted and started over, that's when some more scrap can come. So once again, very similar to continuing a quote unquote normal cycle after a shutdown or after a long shift shutdown, just a disruption in the cycle can actually cause a problem. Many times, just operators I've been watching or helping, takes a longer time to remove a part, one part sticking, then 2 parts are sticking. The press is open for 30 seconds or a minute longer than normal, and the operator just closes up the press and just continues to run the next cycle. Well, what happens is that after a few cycles doing that, the press will not have recovered enough heat during that slightly longer press open time. And as a result, something's cooling off. They're getting a non-cure. They're getting a mold fold. They're getting something that is happening that's not the normal things to happen. And so we need to compensate for the disruption in the equilibrium. It's one thing to consider, well, the press cycle got disrupted, but what you're really disrupting is the equilibrium that the press tries to have by running continuously and consistently. A lot of our presses are obviously square platens or rectangular platens in some way, but the ram of the press is round. And so you have a round peg in a square hole. And oftentimes the round ram is much smaller than the squareness and rectangle issues of the size of the platen and the mold. And so we have molds and platens that are overhanging in the corners of the ram. Our bosses and accountants, they want as many cavities in the mold as possible. So if there's space in the mold in the corners to put a cavity, somebody's going to try to put them in there. And what could go wrong? What could possibly happen? Other companies have kind of got the idea that we don't need to exceed the area of the ram too much with our cavities and kind of stay away from the corners of the cavities. That would generally be a good idea. And so many injection molds tend to stay within more of a round circular pattern. Many transfer molds work better if the pot is round, something similar to the diameter of the circle of the ram. Transfer molds don't work as well when you make them rectangular and square, and even if you put rounded corners in them, they don't work as well. There are issues, there are problems, and if you have a compression mold and you've got the square mold and you run cavities all the way out to those corners, there's usually problems out there. And what those problems are is that very often the corners are not supported very well by the ram. We get into problems with with the plates of the mold or even the platens of the mold of the press. They start flexing and they're not able to distribute force evenly across the corners of the mold. It's also possible that because of cantilever force, something I talk about in my books, and I'm not going to be able to talk about it on here, but if we're not supporting the corners of the press from underneath with the ram, and the structure of the bolster and the structure of the platens, then those corners can flex and come apart and not hold a thin parting line. And so generally, if you have thick parting lines in the corners of the mold, it usually means that you have a cantilever problem. It's a poor force distribution problem. It could be caused by insulator boards. It could be caused by cantilever. There's also a problem in the corners of the mold where that if you have a poor distribution of thermal gradient across the mold, the corners are farthest from anything else and they're going to be more likely to lose heat. It'll be harder to keep them hot unless there's other methods of different types of heaters that would be put in the mold that would actually increase the heat that is in the corners versus in the middle of the mold area. So knowing and understanding why those corners have problems, they can be designed out and they can be minimized by mitigation and countermeasures such as better insulation boards, better designs in the mold, better ways to understand what cantilever is doing to you, and better heat distribution techniques. But that's an underutilized area, is to either eliminate putting cavities in the corners or to make it easier for those corners to work. In the center of the mold is a little different problem that is underutilized and understood very poorly. And that is the center of the mold is where you can have the most heat. You can end up having uncured parts in the corners and scorched parts in the center of the mold, depending on what type of heat system that you're using, be it steam or electric or hot oil and various other things. And so trying to get a uniform thermal gradient and a uniform pressure gradient is very important. And there's all kinds of ways to figure out whether or not you have a uniform thermal gradient by using infrareds, by using thermal paper, and it's fairly easy to understand what kind of pressure gradient you have across the mold by using pressure sensitive paper like from Fuji, or using little lead flakes, or even using other types of paper. There's lots of different ways that we can actually test how consistent that our thermal gradient is and how consistent that the pressure gradient is. Let either one of those get out of balance, and they're probably going to have scrap parts as a result of it. And we usually, because we don't know, sometimes we just run the press anyway and live with the scrap. It's very worthwhile to figure out whether or not you have either of those two issues, and then come up with ways to fix it. People have always a desire to shorten the cycle time. What's my shortest cycle time that I can run? I need to get more parts per hour. I need to get more parts per day. Yield is very important. And press cycles over time, they have a tendency to get longer. We tend to cover a multitude of sins and scrap problems by having longer cycles. Press operators, if you leave it up to them, they tend to like longer cycles because it gives them more time. They don't have to work as fast. They don't have to be right there at the press when it comes down. They might be able to run more than one press at a time, but it comes at a cost. And sometimes we just want to figure out how to make these cycles to be able to be as short as possible. But the problem is the press open time varies because of the operator training. One operator is different than another. The long arms of one operator might be able to demold the parts faster than someone with shorter stature who has to go around to the back of the press to get the extra parts out or something. And so because of various changes and differences in press open time, we end up having all kinds of problems that will result from that. And so if a press is left too long in one way or the other, either left open or left closed, we might have parts that are sticking in the mold and causing variances in the time that the press is open and being serviced, which then changes the dynamic of the pressure gradient or the thermal gradient, causing the parts to have a different state of cure when they're being cured. So we need to investigate that. And so both of these scenarios of varying press open time can compromise the equilibrium of pressure and gradient of thermal gradient that is taking place in the mold. And they need to be examined. They need to be watched. They need to be challenged and understood. Why is it variance? What can we do to mitigate that? Very much across the rubber industry, in my opinion and observation, a very underutilized technique to do. Here's something that, in my opinion, the rubber industry just simply does not understand. We want to reduce cycle time. Now, most people know that to get a certain state of cure, if you're satisfied with your cure time and the temperature that your molding cycle is running at, there's a certain state of cure that you can achieve. Okay, granted. Most people and molders and process people understand that if I raise the temperature just a little bit, theoretically, I can shorten the cure time a little bit and have the same state of cure that I had. If I lower the temperature a little bit, I may have to extend my cure time a little bit in order to reestablish the same state of cure. And there's a lot of experiments about that are available and have been going on for a long time. So theoretically, I can shorten cycle time by elevating my curing temperature if the rubber will allow it. And we do that. People will try to shorten the cycle time by taking it out of the cure time. And that works fairly well. People do it all the time. Process engineers are well known as to coming up to a press, raising the temperature a few degrees, shortening the cure cycle, the cure time, which then therefore shortens the actual cycle of the press from gate to gate. And everything looks fine. Then they walk away, and about an hour or two later, there's non-cure taking place. It's undercured. There's some defect that's starting to show up, and they have to reestablish the previous cure time and the previous cure temperature in order for it to run. Here's what I think is happening. whatever percent that you shorten a cure time, say you shorten it by 10%, if you do not shorten the press open time by the same percent, then you will not be able to maintain the benefits of the cure time reduction. So what that means is if you've got an operator that takes a certain amount of time for the press to come down, shuttle out, remove parts, load new parts, or clean the press and then close the press back up, that takes a certain amount of time for that operator to perform that function. If you simply take a few seconds or longer out of the cure time, a percentage, 10% out of the cure time, then you've got to get into that operator's function of the press open time and find a way to reduce that by 10% also, or you won't be able to maintain over time the shorter cure time. The shorter cure time is there, any of the cure time, a significant function of the short cure time, of the cure time at all, is to recover the heat that you lost during the press open time. And so, yes, theoretically, if you're putting more heat in there because it's now a higher temperature, you may need more time to recover the heat than just the higher temperature can provide in the shorter cure time. And so there's a trade-off that has to happen. And if you cannot shorten the press open time, you may have to do some other countermeasure to be able to take advantage of that shorter cure time. It's lost. That's an underutilized understanding that people just they don't recognize that as being something they must do. And I encourage you to work on that percentage conversation with your process when you're observing it. You can't just simply shorten the cure time and necessarily get away with it. There are issues with a longer than standard press open time when it happens. If the press time open, the service time of the press is longer than normal, then unnecessary scrap will resort because the operator closes the mold and just simply starts the next cycle without letting the press heat up and recapture that heat before going on to the next cycle. And I see this all the time. It's either usually with new operators that haven't been trained to close the press up and let it regain heat before starting the next cycle if it was open for some period of time that it shouldn't have been, or it's someone that doesn't care. They just running it. They're just marking time on the job. And so usually there's some operator training that's required to mitigate that problem so that when press operators have a problem that they have actually had the press open, instead of 2 minutes, it's now open 3 minutes. They think, well, that's not too bad. No, that's actually a lot of time from a heat loss point of view. And your normal cure time then is not enough to recapture all of the heat. And it might not show up on the first cycle, but it most certainly will start showing up on second and third cycles down the way, depending on how long your actual cycle time and cure time is. This brings me to something that I refer to as being the value of 1 second, the value of 1 gram, the value of 1%, meaning that most companies have no idea what the value of 1 second is. If you could take 1 second out of your cycle, if you could take 1 gram out of your waste, if you could take 1% off of your cycle or off of your waste or off of your time, there's usually a way to do that. I go up into clients many times about their process and say, oh no, there's no way that we can shorten the cure time. There's no way we can raise the temperature. There's no way that we can make the cycle time shorter, because if there was, we'd have already done it. I get that a lot. And yet they won't have actually looked at how slow the press is opening and how slow the press is closing and clamping. They won't necessarily look at how slow their injection time is and the things that they can do to mitigate that or to shorten it. Even just 1 second, there's a lot that can be done. So I have an example here that, for instance, if you're running 50 hours 50 weeks, 2 weeks a year that are vacations and not running, and you're just running one shift a week, and it's only for the 5 days of the week, you can come up with a whole lot of seconds during the course of the year. And if you took off a few seconds of each cycle, you end up with a lot of extra cycles. And every one of those cycles, if you step back and say, well, here's how fast we're running this mold right now. This is how many cycles we get in a year right now. And therefore, when you're pricing it out from a corporate point of view, all of your time, all of your direct labor, all of your indirect labor, all of your press time, all of your power, all of your utilities and burden and everything are completely covered by however it is that you're running the press right now. But if you start taking a few seconds out of each cycle, and then that means that all of those seconds are accumulated together and you get a bunch of extra cycles. The only cost for those cycles is just the material, because everything else was already covered. You make a lot of money on those cycles that you got extra for it. And so that helps you to understand, what is the value of 1 second? What's the value of 1 gram? What's the value of 1% of improvement as you go along? It stacks up in ways you almost can't imagine. Hardly anybody ever looks at it that way. I encourage you to think about it. Just might impress you. I mentioned earlier that one of the waste factors that really trouble people is shelf life. We end up trying to run material that's, well, the reason we got all this scrap is because, well, maybe it's expired. Maybe it ran out of its shelf life. How long is its shelf life? In fact, I get the question many, many times, how do you determine, how are we supposed to know how long this material is good for before we can't use it? And usually the way they know they can't use it is they're trying to run it. And so they're creating scrap, and then they're finding out they can't run it well, so they end up throwing away however much rubber that was to replace it with something else. And so there's a lot of seemingly unnecessary waste that goes into running material that has expired its shelf life. And so while there are good ways to determine what the shelf life is and whether or not the rubber is usable and can be refreshened or anything like that, it becomes the root cause search of, why is it that the shelf life is short? What happened to it? And a lot of times that has to do with how it's stored. And so people inevitably store material in humid conditions and environments without understanding what hygroscopic nature might be involved in the rubber or some of the ingredients of the rubber. They end up storing ingredients or the rubber preforms or raw stock in the top of high bay areas where it's very, very hot. And so they're getting a accelerated low grade of cure taking place that is robbing shelf life out of the material. Most people simply around the world, even though they know about it, they don't have a cool room. And I do mean a difference in a cool room versus a cold room. It might feel cold compared to the outside, but cold is something that is below 15 degrees C, and cool is a little bit above that, 15 to 18 degrees C, for those of you on centigrade. And so we need cool rooms. Say, well, I've got room for a cool room. Well, there are ways to make a cool room on the lowest section of high bay racks so that you can enclose the lower section of a high bay rack on the floor, insulate it, stick your gaylords or your forklift pallets of material into that lower section underneath the lowest rack of a high bay rack, and have that enclosed from the environment, even sticking a little air conditioner or a humidifier or both into that area to make a somewhat controlled climate, therefore extending your shelf life of material much longer than what you could have done in the environment that they're in. I consider this to be another underutilized option for people. A lot of companies around the world, especially in Asia, low-cost labor areas and whatnot, we can't afford to have operator assist devices. Can't afford robotics for sure. We just can't afford that. We'd rather throw people at it. And what people do on their own with manual labor is usually inconsistent. And I especially think of things like having a multi-cavity mold, and I'm using my hands to load preforms into every cavity. And I use the example many times of if I wanted to have 16 eggs all fried at the same time at the same level, but the only way I could get the eggs onto the griddle was to load egg 1, load egg 2, crack open egg 3, crack open egg 4, dot, 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 crack open egg 16. By the time I cracked open egg 16, egg 1 may already be well done. And my objective of being able to cook all of the eggs evenly and serve them at the same time in the same condition is completely obviated. It can't happen. And so something like that to its own scale is when I put preforms in one at a time manually and go back and get some more and place them on the mold in some order within the mold. The preforms that went against the mold first see the most heat the soonest and are sitting there until the last part goes in. Whether I dump them in as a pile and then start spreading them out, the point is all of the preforms did not go into the cavity and touch the hot surfaces of the mold at the same time. And that's where slip sheets, loader boards, other devices that will allow for the opportunity for all of the preforms to come into the mold surfaces at the same time and achieve somewhat better chance of having the same state of cure at the same time than if we do something without an operator assist. If you only have one cavity, okay, you don't need to do it. If you only have two cavities, okay, chances are you can deal with that. But as soon as you have more, there's often a problem. And obviously there are more and more expensive and more elaborate ways to do something, but trying to find creative operator assist methods to bring about consistency of the loading of the materials into the mold does reduce waste. It does reduce scrap. It does reduce cycle time because it's more consistent and you have a better chance of maintaining an equilibrium than you would have had otherwise. And so the potential of saving 1 gram, 1 second, 1% is very much a real thing that you can take advantage of by looking at that. The operator assist devices are methods to load and place preforms. Generally, we have a situation with most companies will say, well, I can't afford it, but if you do the math, you may find that you can't afford to not do it. Another problem that we have with not being able to maintain our thermal gradient and our pressure gradient is because of the condition of insulator boards. The purpose of the insulator board that's placed between the platen and the bolster of presses is to minimize the amount of heat that transfers from the platen into the bolsters. And those are often damaged over time. I go into clients all the time around the world and walk up to a press and see the insulator board with a crack right on the front. I can see it on the front edge. And I'll ask a process engineer or a maintenance person, how long have you been here at the company? Well, I've been here for 10 years, you know. Have you ever replaced these insulator boards? No, we haven't. Well, according to the people that supply insulator boards, they might say that you need to replace insulator boards once a year or once at least every 2 years, which is convenient for them because they sell insulator boards. But the truth is, usually if it's a press that's been running continuously at high temperatures, you need to be checking the insulator boards at least once every 2 years and possibly replacing them after 3 years, because what happens is they start degrading. There are volatiles that come out of the insulator boards and it makes them what they're normally fairly hard and kind of brittle, and so they begin to crack. If you actually see a crack in the insulator board, I believe that you probably should have replaced it 2 years ago. A lot of companies their motto is for maintenance budgets that when the cracks get too bad or when a piece of the insulator board falls out, they will choose to put it on their budget for replacement next year. Okay, well that's actually not a good plan. You are hurting yourself with thermal gradient and pressure gradient all day long, every cycle with whatever you run in that mold, and you're not achieving what you want. Chances are I've had many examples where people would not even realize they had a problem, and they would go ahead and replace the insulation board and find out that all kinds of problems were improved. Quality was improved, flash thickness was improved, meaning less or more consistent. Tear trims came off easier. There's lots of stuff that they didn't actually realize was related to dysfunctional, compromised insulation boards. Most of the insulation boards that we have on presses came from the press manufacturer. Well, if the press manufacturer is trying to minimize their cost of the press to you and make more money, it behooves them to put a thin insulator board, 1/4 inch, 25 millimeters, rather than something that's actually worthwhile, more like 25 millimeters or an inch thick. Because that insulator board costs more money, and they can save money on the press they sell you by putting in a thinner insulator board. Well, that may not be your best option. And so if you're buying a press and you were to specify, I'd like a 25 millimeter thick insulator board, they say, well, that's going to cost you. Well, maybe it should, because then if you get a thin insulator board, it's costing you anyway. Now it's costing you with every heat cycle that you run for however many years that you're trying to use that insulator board. And so it's better to go up front and do it right to start with. I also recommend a material that's called a Pyropel is a brand name. It's a polyamide material, MD60. And I recommend that sheet be placed between the platen, the heated platen, and a typical insulation board. This material has some flex to it, which the traditional insulator boards does not have, and it has better thermal diffusivity. It's a word about materials. Very likely none of you woke up this morning wondering, how can I use thermal diffusivity in a sentence? But all it means is that's how fast heat travels through something. We understand that travel of heat through aluminum and through copper is very, very fast, faster than heat passing through steel. But passing through the insulation materials, it's passing through very slowly. And so the Pyropel type of material, these polyamide fiber boards, the heat passes through them slower than it does the regular insulation board. So if you sandwich one of those polyamide fiber boards between a platen and the insulation board, that is harder for heat to get to the regular insulation board, which means it lasts longer, and the slight flexibility that is in the polyamide fiber board will take some of the flexing forces that often then crack the relatively brittle insulation boards. It makes them last a lot longer. I have a program that I've come up with over the years that I call STATS. And STATS stands for a scan, a temperature, and time set. And what it's really doing is saying that, okay, I know I have variability in my press open time. I can't help it. It's just gonna happen. And so if in advance of that process cycle, I've done some process engineering and perhaps used a solvent swell test and other methods, that I want a certain state of cure for my part. It's imperative that I have a certain state of cure for my part, or it won't actually provide the function and requirements that the customer needs. And so I know that if I have a certain temperature and a certain time, it gives me the state of cure that I need for a functioning acceptable part. But if my press open time varies, sometimes longer, sometimes shorter, for reasons I cannot avoid, then I know that for my standard set point on the press of a certain time and a certain cure temperature, I'm not going to maintain consistent state of cure. So what this says is that, okay, I'm going to pick a spot. I'm a process engineer doing a test. I'm going to pick a spot on the press, and I'm going to take a temperature. It might be with an infrared non-contact, or it might be with a contact that is on the press, usually on the top of a core, on an edge of the mold right beside where the cavities are. We pick a spot. Especially with infrared non-contact, those are often a little bit incorrect heat because of the reflective nature of the steel. And so by creating a little patch on the mold that is roughed up with it, like a little bit of a texture to it, and then paint it black with a high temperature black paint. I can take the temperature of that with a infrared, calibrate it to an offset, and actually know what that temperature is and be a consistent temperature. And so whether this is an automatic thing that I'm taking a temperature of right before I start a cycle, or if it's a contact that I take a temperature of in this spot, and I record that temperature and I find the correct cure time for a given temperature, shorter or longer, that gives me the state of cure that I want. And I can go through and make a chart. And so let's suppose that I wanted my mold temperature to be 350 degrees. I think that's going to be like 175 degrees C or something like that. But it's whatever your molding temperature is. I know that if I have my given cure time, then I get my certain state of cure. If my press open time is too long, then when I check the temperature of that spot right before I close the press, if it's a little bit lower, maybe 3 degrees lower, I know that to achieve the same state of cure, I need a slightly longer cure time. If it's a little hotter for whatever reason, I know that I need just a slightly, it may only be 20 seconds, 10 seconds, 5 seconds shorter cure time to achieve the same state of cure. Therefore, with some process engineering tests and using perhaps swell tests, solvent swell tests to determine the actual state of cure, that I can create a chart that if the temperature is this, my cure time should be this. If the temperature is this, my cure time should be this. And they may only vary very small amounts. But if I had that chart, then I can do one of two things. Then before the operator is ready to close the press, they take a temperature of that spot and then adjust the cure time manually for the cycle, and they get the cure time that is needed for that state of cure. Or you could have it done with a positioned infrared non-contact on that spot and have a separate PLC running in the background that is reading that temperature, if then that, and it automatically plugs in a cure time for the cycle accordingly, and you can end up having a state of cure that's constant and maintained. And so that's an underutilized way to do that, but you need to create a time temperature chart and involve some concept of the stats. And in my latest book, the compression book, I have a whole series of an actual ladder logic program that can be implemented with a PLC for both that one's a compression mold, but there's versions of it for injection and transfer molding as well. The concept, though, in the principle, is to take a temperature of something on the mold and adjust the cure time accordingly with the temperature. It's easy to adjust cure time. It's not so easy and quick to adjust temperature. So the cure time is the one that you want to adjust according to a temperature that you actually take on the mold. What I call micro tear trims. This is the idea of what's the value of 1 gram. There's a lot of companies that they interchange the word tear trim and overflow, especially for something like compression molds. They interchange those words as being the same thing. They're not in my opinion, and not in my practice and experience. And so most people understand that the tear trim is for tearing off. It needs to be filled completely, but the overflow does not need to be filled. If you have a large tear trim or somehow a large overflow that you're trying to fill every time, in my opinion, you're wasting material. You can use not in the mold that you've built, but the next one that you build can be designed with a smaller tear trim and an overflow that's not going to completely fill. Therefore, you're using less rubber. And so other rubber companies have come up with some standards of a tear trim that is this size, a certain size. They've got a certain tool that's designed to make a certain tear trim, and that works very well. And so they kind of stop right there. There seems to be very little work that is done to take that tear trim and let that tear trim be the size of an overflow, and then smaller than that, make a smaller tear trim. Tear trim is supposed to fill, overflow is not supposed to fill. And so by considering your normal tear trim to be an overflow and creating the design of your mold to have a micro tear trim, something that's smaller, now you're taking a gram, you're taking maybe a lot of grams out of your rubber cavities from that particular mold design. We don't tend to, we somehow don't think about of doing that, and there are some very clever ways that can be done to good efficiency. And I encourage people to try to utilize that concept in your future mold designs. The idea that transfer pots leak rubber out between the clearance of the pot and the plunger. If you don't have clearance between the pot and the plunger, then you won't get them together. And if you do ever get them together, you won't be able to get them apart. But there are ways to have effective leakage mechanisms that would minimize, if not eliminate, the leakage that comes from the pot. Rubber tends to flow on the path of least resistance. And so when you have a transfer pot that is leaking rubber and causing non-fills somewhere within your parts and your cavities, the first thing that people try to do is they just try to put more rubber in the pot. What they usually find out is that more rubber leaked out and very little of it actually went into filling cavities because of the path of least resistance. If rubber is going somewhere that you don't want it to go, it's going there because it was easier to go there than where you want it to go. So we have to find ways to hinder the rubber from being able to go in places that we don't want it to go. And there are lots of ways to do that. You don't just have to live with excess rubber that's flowing out of your pot. And so an underutilized technique is finding ways to change where the flow of the rubber is going to hinder it from being able to go in places that you don't want it to go, and wasting rubber where you don't want it to waste. Another thing about transfer pots, I definitely was, 40 years ago when I got into the rubber mold and rubber mold design and things like that, I was taught by some very wise people, and they pretty much said that, man, you got to have a pot that completely covers over all of your cavities. You really don't want your cavities to be sticking out from underneath the shadow of the transfer pot. I've long since found out that while that is good advice, it's not the only advice. There are very often times when the shape of my cavity layout, the shape of the parts that I have, allow me to have more than one pot in the same mold at the same time. And so if I have a large pot, big square with rounded corners, I might be able to have 4 separate pots that are smaller and round within that same thing, and there might be a cavity or a cluster of cavities underneath each pot. If I have multiple pots within the mold at the same time, each pot has to be a little bit deeper than normal because I have to somehow get all the rubber in there. But it means that from a flash pad point of view, when I get done with the flash pad, however thick that it might be, if all the pads are the same thickness as the big one used to be, then I have less rubber that I've used. It's like die cutting 4 circles out of a big rectangle or square, and I have less rubber left over in the pad. It's a way to try and take grams out of the cycle. If I take grams out of the transfer cycle, I've also taken seconds out of the transfer time, and so that can be very helpful to the process as well. In addition to that, if the idea of using multiple pots works, we'll assume for the purpose of this discussion that it does. I've had a number of parts that will say that across the whole mold were very, very large, took up a lot of space in the mold, but the sprue point in order to get the rubber into the cavity was maybe off to just one side, and the sprues came in over here and had to flow all the way across into the whole part, and that's the way it had to be filled. There's all kinds of reasons that parts are made that way and they have to be sprued that way, but the traditional design was I had to make a pot that is that big in order to go over the whole pot. So as a result, what happens is I put all of my rubber into this big pot, and all of it has to manage to flow over to these 2 sprues. Well, I'm a lot better off of just having a small pot around the sprues. It's a deeper pot, and the only rubber that is going in is just over where those sprues are, with plenty of room around them. And I transfer my rubber without it having to run a long ways across a big pot, just because of the theory and understanding that my transfer pad must cover the entire part. I've challenged that, and I find that that's not really what I have to do, and I can get a better part by having more centralized and located over where the sprues are, wherever they may be, rather than over everything. I use less rubber, I transfer less rubber, I transfer it in less time, things like that. There needs to be a balance in injection molds between the runner and its fill capabilities. In injection mold design in a lot of countries, like for instance Europe, been doing injection molding for many years, just decades and decades. Pretty much the same in the US. In the US, injection molds started for the most part, being fairly widely used in the 1990s, and so there's 30 years of ever increasing injection mold experience and tool design and process design that's been going on in the United States, and at least 10 years more than that, a decade or so more than that in Europe, with good experience. In Asia and parts thereof, it's not quite as advanced in many ways, and yet they're learning from the experience that has already gone before in Europe and the US. And so there's a faster learning cycle, but there's not necessarily an understanding of why some of the principles of the design should work and will work. And so one of the real things that I have found helpful is to try and figure out some kind of balance between the runner feed size and the fill capabilities. If we make our runners small in diameter and volume size, which is an objective to have less waste, then we may be introducing a restriction to the rubber flow that causes other severe problems. Some materials scorch easier than others. If you have too much shear, if you're trying to push the rubber too fast through whatever size of runner you have, whatever size and shape of gate and sprue that you have, we introduce problems with our design that we don't necessarily know that we have. We just start, we design something and live with it, think that it's okay, and we don't necessarily experiment beyond that. And so finding that balance that, okay, well, if I increase my runner size here and there, I'm wasting more rubber through engineered waste. Yeah, but I might be actually filling the part faster and better so that I more than compensate for that with a faster cycle and less waste in the form of scrap for whatever reason. So we have to balance that in order to find a balance, and every part will be different, every mold will be different, and so it is something that is born by experience. But if you never look for it, if you never evaluate it to start with, then what you don't know is what you don't know. When it comes to injection runners, mold designers, mold builders, and process people will say, well, I can use less material if on the runner plate, if I have a hot runner, if I only cut the runner into one plate instead of cutting it into both plates. I save time. I don't have to set up both plates to match and marry and mirror a runner design. I just don't have to. I save money. That way you spend less money on the mold to start with. In my opinion, that when you do that, you're pretty much likely going to end up with a half round runner, because that's easy for the mold builder to use, because we use ball-end mills, and they don't have to have a special cutter. They just use a ball-end mill. What most people don't fully understand is that a half round runner is one of the most inefficient runners for flow that you can make. There are worse ones, but that's one of the more inefficient ones. And so by using that half round as a standard without making something else, you say, well, I'd really rather have a trapezoid runner because it releases from the mold easier. It's going to be chargeable. But even a trapezoid runner, all things being considered equal, is not a very efficient flowing runner, even though it pulls out of the mold easier. So most people would understand that a full round runner, instead of a half round runner in the mold plate, full round runner flows better for rubber, and it does. And there's a reason for that. There's a reason that we use a round pipe when we're pumping water or oil or gas or anything else in it, because it's just geometry. In a round pipe, the area and volume of something round is the greatest amount of area or volume to the least amount of circumference that is encapsulating it. Every other shape is worse. And so as we have rubber flow flowing through something round, I have the most volume of rubber flowing through that round shape in contact with the least amount of perimeter of hot mold that's trying to cure it and scorch it and hinder its ability to flow. That's why a round runner is actually better. But a round runner means that I've got to set up this plate and machine it. I've got to set up this plate and machine it, and I've got to make sure that they're lined up and mirrored. I have lots of extra cost, and that's passed on to the buyer of the mold, or to the seller of the mold, to the customer. And you know, if you're comparing mold costs from one machinist or one mold builder, if the customer is comparing mold costs from one company to another, you might price yourself out just because you put a round runner in it. But then you pay for it over time. And you say, well, the customer won't pay for round runners, so we can't do it. But yet you're absorbing the cost in inefficient flow, scrap that might come from that, excess time of longer than necessary time for injection speed. You are paying for the difference in this cost, and it'll be a lot more over time than the cost of just going ahead and make it a full round to start with. When I have to machine runners into just one plate, I have done extensive studies and research projects related to different types of cross sections of runners. And even though I know that a full round runner works the best, there are sometimes I have no choice but to cut a runner into one plate and not the other plate. And so I've developed and tested something that I call a polyarc cross section. And this that you see on this slide is the way that you make the polyarc. Polyarc means there's more than one arc, more than one arc. And so I have two different spots where I use a radius of 1, and then I make a tangent spot between this R2, and that gives me a particular design of the cross section of the runner. It's easy to figure out. You have to grind a cutter, usually starting with a ball end mill and reshaping it and regrinding it to be this shape. And as a result, this runner flows better than half round, flows better than trapezoids. It nearly releases as good as a trapezoid, and it nearly flows as good as a full round. It's not a full round. It doesn't flow as well as a full round, but it's close, and it's a lot better than half rounds or trapezoids by themselves. And so you might take a look at this and consider that. Again, it's an underutilized technique for being able to have better flow within the system of the flow of the cross section. A lot of people, again, to save cost, when you have an injection hot runner plate, there's a tendency to not provide precise registration for those plates. As a result, runners can get off center, offset with a lateral shift to each other. The downcomer sprue from the injection press can get offset so that it's not aligned, and you say, well, who cares? We're going to throw that away anyway. Well, it turns out that in many of the tests that I have run where I start deliberately offsetting a runner or a downcomer sprue, is that I find that for basically every 1% of lateral shift, I get as much as 5% restriction in the flow of the rubber. And so if I'm offset 5 or 10%, I've got a lot of restriction for my rubber, because the rubber, as it flows through an offset runner or try to come down through an offset sprue, it doesn't, the laminar flow is hindered dramatically by the corners, the dead spots that form there. And so we need to spend some time and make sure that the money, well, but the customer won't pay for it. We're going to throw this away anyway. What does it matter? If this gets bad enough, it matters to your every single cycle that you're running. And usually what happens is, if you've got the ability for the runner plate to get shifted laterally, every time you put that mold in the press, it might be offset one direction and then offset another direction the next time you put it in the mold in the press, and then sometimes it happens to be aligned, and your process won't be the same. It's worse if it was mismachined to start with, meaning that when they set up, the machinist set up on this plate versus setting up on this plate, they didn't take the time to marry the actual layout of the runner, and they end up getting shifted. The mold plates weren't shifted; the machining was shifted and not matched up. And that's in my opinion, a terrible situation for ongoing flow and usage of that runner system. CRBs are cold runner blocks. Cold runner blocks have been used in Europe for easy 30 years. Extensively, and more extensively now than ever before. Cold runner blocks have been being used in the United States for almost that long, but have really started coming into use in the last 20 years. A number of different machine shops make cold runner blocks, but all cold runner blocks are not created equal. They're not machined equally. They're not designed equal. They aren't necessarily friendly to use. There's very little, there is some, but there's little use of cold runner blocks in Asia, in South America, in Central America, and places other than that. And most of that is because, well, we can't afford a cold runner block. They're too expensive. They might be. They're not for every product for sure. But compared to the price of an injection press, a cold runner block is actually not that expensive. And so if somehow a company has managed to justify the acquisition of an injection press, it is more likely that you can justify the acquisition and design and procurement of cold runner blocks. It's not for every mold. You want cold runner blocks that can be used on a multiple sizes of molds that would utilize it all eventually. Sometimes, and not that often, sometimes you have a mold that you're going to run all year long, and so it's easier to justify a cold runner block on one of those molds. But sometimes you have a mold that would only run for 1/4 of the year, 3 or 4 months out of a year. Well, I can't afford a cold runner block for that mold. My customer won't pay for it. Sometimes we got to invest in ourselves and look at our molds, look at how they're designed. And if I have a cold runner block that has 5, 6, 7 months of excess time, I start designing new molds to fit the cold runner block and start taking up more of its time. Molds that in and of themselves would not justify a cold runner block, but boy, you start saving some money and some time by adding it to a cold runner block. And the benefits of cold runner blocks are also not very well understood. If you did better understand the benefits of a cold runner block, it becomes a little easier to justify. One of those is the fill time. Well, in a hot runner mold, you have to actually flow rubber through the entire runner system before it gets to the cavity. In a cold runner block, you really only have to flow rubber from the nozzle drop of the cold runner block into the cavity. So the fill time is shorter. The material usage is less. The amount of cure time and cycle time can be greatly adjusted to your advantage, because now you're not trying to balance the runner being cured up and still being able to get the runner out versus only concentrating on what temperature do I need for the cavity itself, because that's where all the work is for the rubber. And there's a lot more, but those are reasons that you would want to investigate more about using a cold runner block when you haven't been. It's a bit of a shameless plug, but these are 2 of the books that I have written. The Green Book's been around for a number of years, published by Param and Technobiz, and the Blue Book on compression molding of rubber has come out just last year and is being widely circulated. And there's a lot of these copies around in various places. I encourage you to get a hold of a copy. There's good information, useful. A lot of the things that I've been talking about today are also further discussed in these books, and they'll help you in a lot of areas that you might not have been able to get a hold of. I really do appreciate the opportunity and your patience in listening and to this instruction, and I wish you all the best. I wish I could be there in person to take questions and answers, but I can't. And so for that, I regret not being able to see everybody face to face and thank you personally and entertain your questions. But there's an opportunity to connect on one means or another, especially through my books or through some other training program at another time. So with that, I bid you a farewell, and I wish you all the best.